Well, let's finish up chapter 13, and this last topic we want to talk about is the idea of latent heat. Now, when I gave you a definition for heat at the very beginning of this chapter, we said heat is just another form of energy, and the definition said that it's the energy that is exchanged because of a difference in temperature or in a phase change or a change in phase. So we've dealt with this, the heat that's involved in a temperature change. That's when we've used our equation Q equals mass times specific heat capacity times change in temperature. But what we haven't dealt with is the heat that's involved whenever you have a phase change. We actually talked about this back in, I had a note here, I think it was chapter 6, where we said that whenever phase change happens, yeah, it was chapter 6, that whenever there's a phase change, the temperature of the substance doesn't change. So if you look at this, what we call a heating curve over here to the left, you'll notice that we've got these periods that are where we've got the angles like this period and this period, this portion of the graph here, but then we've got these flat areas right here. And notice on these flat areas that the temperatures for those flat areas, it's 0 degrees Celsius down here at the bottom and 100 degrees Celsius up here at the top. And so this is a heating curve for water. And what happens at 0 degrees Celsius and 100 degrees Celsius? We know that water freezes at 0 degrees Celsius and it turns to a gas or vaporizes at 100 degrees Celsius. And so that's what those flat areas are representing. Notice that our axis, that looks like our y-axis on our graph, represents temperature. And so the temperature just flattens out and doesn't change at 0 degrees and 100 degrees Celsius because the water is changing phase at those temperatures, right? So what we've learned so far is we could talk about what Q looks like in this area here and what Q looks like in this area here because there's a temperature change. And these are areas where if we were going to calculate the Q, it would be just M times C times change in T, just like we've learned before, right? These are the areas that we learned how to calculate heat, but we don't know anything yet about calculating heat at these areas where the curve is flat. And so we have a new formula for that, and it's the formula for latent heat. All right. So the formula for latent heat, let's first talk about the definition. The definition for latent heat is it's the amount of heat absorbed or released by a substance during a phase change. Okay. And so the formula that we have for that is that Q equals the mass times capital L, and we say right here that capital L represents latent heat. So that's something I'm going to have to give you. It's not something that you're going to memorize or just automatically know. But if you want to find the heat on these portions of the graph where it's flat and a phase change is occurring, you just need to know the mass and then whatever that value is for latent heat. Now, it's not going to be the same value at these two flat areas here because a different phase change is happening. Here, this is where water is, in this case, because the temperature is increasing over time, this is where the water is melting, right? It's changing from the solid phase, ice, into its liquid phase. And so anytime you go between the solid to the liquid phase, which is what we call melting, or the liquid phase to the solid phase, which is what we call freezing, you're going to use L with a subscript F next to it. Now that F stands for, it would be nice if it stood for freezing, but it doesn't. It stands for the latent heat of fusion. Okay, so the latent heat of fusion is what you use if the water is freezing or if the water is turning from solid to a liquid. So anytime there's a transition between that solid and liquid phase in either direction, we're going to use LF, the latent heat of fusion. But if we're up here at the top of the graph, where in the way our graph is laid out, that water is changing from liquid to gas, we're going to use what do we call that? We call that vaporization. This one's nice because the little subscript makes sense. So we're going to use LV, which is the latent heat of vaporization. So if you go from liquid to a gas, use LV. If you go in the reverse direction, which is where it condenses from a gas to a liquid, we're also going to use LV. So anywhere up around this 100 degree Celsius mark, we'll use LV. If we're down here at the 0 degrees Celsius mark, we're going to use LF. Okay, so now we have formulas to figure out the total heat exchanged or the total energy required to, in this case, take water and go from -8 degrees Celsius, which is our lowest point on our graph, all the way up to 100 degrees Celsius. And notice it's not just when it hits 100 degrees Celsius right here. It's actually, the curve is drawn to where it goes on out a little bit further over time this way. That's because we're totally vaporizing the water. So this particular heating curve is, I've drawn it this way because it goes along with example 13.5 in the book. And so I just want to walk through that just to make sure that you understand. If I gave you a problem like this, that you'd know how to find the total energy required to do this. And so how does the problem read? The problem says we have a 125 gram ice cube. All right, so they give us the mass at the beginning. The mass is 125 grams. And they tell us that the temperature, it starts out at -8.7 degrees Celsius, which is exactly what I've drawn over here, right? And at 1 atm, they give us the pressure. Now, pressure, when you look at that, you're like, oh, how am I going to use that? You don't actually need it. That's kind of extraneous information that they throw out there to maybe just kind of throw us off. But it is telling us that we're at standard pressure, right? Remember STP that we learned in the previous chapter was 0 degrees Celsius and at a pressure of 1 atm. So this is standard pressure, standard atmospheric pressure. At this standard atmospheric pressure, how much energy would it take to turn all of the water in that ice cube to vapor? And so we've drawn a graph a heating curve to represent that, right? This is our heating curve for that problem. The ice goes from -8.7 degrees Celsius. What's it going to do? The temperature is going to be raised over time to 0 degrees Celsius. At that point, it's going to level off because it's going to begin melting, the ice is. Once it's fully melted, once it's fully changed to that liquid phase, then the water, which is now liquid, is going to start heating up again, right, all the way to 100 degrees Celsius. And at 100 degrees Celsius, the curve is going to flatten out again as all of that water changes, that liquid water changes to vapor. All right, so that's what we've basically got 4 Qs that we've got to figure out. And then we'll add all of those together to get the total energy required, or the total heat exchanged, to take this 125 gram block of ice and heat it up from -8.7 degrees Celsius all the way to 100 degrees Celsius and fully through the phase change. So what I'm going to do, just so that we can keep up with all of these Qs, is I'm going to label them Q1, Q2, Q3, and Q4. All right. And then, like I said, the total Q is going to be all of those added together. So what is Q1? Well, Q1 is going to be the mass, 125 grams, right? The mass, by the way, is going to be the same throughout. We're not losing any mass as this thing is changing phases. So we're going to have the same M value each time. For C, we need to know what the specific heat capacity is of solid water, right? We memorized the specific heat capacity of liquid water, but we don't know the specific heat capacity of solid water without looking it up, or it needs to be given to us in the problem. And sure enough, in the problem, they tell us that C for ice, for solid water, is 2.093. So we're going to write that down there. This has our typical, strange units, kind of busy units with joules on top and grams per degree Celsius on top. That for space, I'm not going to write those down. And then what's our change in temperature? Well, if you think about it, the change in temperature is the final temperature minus the initial temperature. And for this part of the curve, right, just for this portion right here where Q1 is, for that part of the curve, our final temperature is 0 degrees Celsius. And our initial temperature was this -8.7 degrees Celsius. So we're going to have 0 minus, which is our final temperature, 0 minus a -8.7 degrees Celsius, which was our initial temperature. So this is our final temperature, 0 degrees Celsius. This was our initial temperature, -8.7 degrees Celsius. And that's nice the way that works out, because it's going to give us a positive value for our change in T. So our overall Q is going to be a positive value. And so when we do the calculations for that, we get that Q1 is going to be equal to 2,300 joules. 2,300 joules once we round for significant figures. All right, so that's Q1. What about Q2? All right, Q2, we're going to get to use our new formula, which is mass times the latent heat of fusion. So we've got 125 grams again. But this time we use LF, which they gave us in the problem, and they told us that LF was 334 joules per grams. Just because this is new to us, I will write that down, joules per grams. Notice we don't have, in this 2.093 value, we had joules per grams degrees Celsius. But since this latent heat does not involve a temperature change, there's no Celsius unit in there, right? So these units will work out great because our grams will cancel out and we'll be left with a final value of joules. And when we do the math with this, we get 41,800 joules. All right. Now we're moving on to the next part of our curve, the largest portion of our curve here, where it goes from 0 degrees Celsius to 100 degrees Celsius. We called it Q3 in our drawing. We're back to using this equation, right? M times C times change in T. M is again 125 grams. This particular C, the specific heat capacity, is that of liquid water, which we've memorized to be 4.184 joules per grams degrees Celsius. And then finally, what's the temperature change here? I'm not going to write it down. It's just obvious what it is. It's 100 degrees Celsius at the top, 0 degrees Celsius at the bottom. So the final temperature is 100. The initial 0, 100 minus 0 is 100 degrees Celsius. So we'll just write that down right here. That's our change in T. And we get a final value for Q3 of 5.230. 5,000. Wait a minute, that's not right. They listed in the book as times 10 to the 4th, so it's actually 52,300 joules. Make sure we got all the math right for that. That looks correct. All right, so we've got one more Q that we need to calculate. That's our Q4 up top here. That's going to be the mass, again, 125 grams. This time it's the LV, the latent heat of vaporization. And they gave us that in the problem and told us that it was 2260, yep, 2,260 joules per grams. Again, grams cancels out. We're left with a value in joules of 283,000 joules. That's our biggest one yet. 283,000 joules required to vaporize all of this entire block of ice here. So this is going to give us a QT. Again, QT is going to be, Q total is adding all these up, Q1 plus Q2 plus Q3 plus Q4. And when we do the math with that, we get 379,000 joules of energy that is required to fully melt 125, whoop, that line went crazy there, to fully melt 125 grams of ice. All right, that's the total energy required. So let's think about that for just a second. Was that energy absorbed or was that energy released? Now, because we're melting it, we might think, well, we must have released that energy because melting is going to require us to add heat. And so energy must have been released, right? No, because we did add heat, but we added heat to the ice. So the ice had to absorb that heat in order for it to melt and eventually be vaporized. So when you're going from a solid phase to a liquid phase or a liquid phase to a gas phase, in those cases we absorb heat because the substance is heating up in order to go from those one phase to the next. But if you go in the reverse direction, if you go from a vapor phase and you condense it down to a liquid phase, or if you go from a liquid phase and you freeze it, right, and turn into a solid phase, in those cases we're having to release energy because we're getting colder. So it's maybe the opposite of what you would think. But the interesting thing about that is when a substance freezes, it actually heats up the surroundings. And so that again is kind of counterintuitive, but it has to absorb energy in order to it has to release energy in order to freeze. And so when it gives that energy off, it actually heats up the environment around it. So that's pretty cool. When water freezes, it actually heats up its surroundings. All right, so 379,000 joules would be the final answer here. That was the amount of energy that was required to melt, to vaporize a 125-gram block of ice. Pretty cool. 4 definitions, and then we'll be done totally with this chapter. So we are almost there. The definitions are probably definitions that you've heard before. Exothermic. What is an exothermic reaction? If I could spell it, let me redo that. I got a little bit. Thermic. There we go. Exothermic reaction is one that a chemical reaction that releases energy. I wish I could spell this morning. Releases energy. And it's starting to thunder outside. I'm distracted by the rain. So what's a chemical reaction that's exothermic that you've probably got some familiarity with? If you've ever been hunting, or we use it when we go skiing, you ever use those things called hot hands, right? So it's a little package that you crush up, and when you crush it up, a chemical reaction takes place inside there, and it begins, that little pad begins to heat up, and so you can stick it inside your gloves, or usually inside your gloves, or even I guess you could put it in your socks to kind of warm up your feet. They just say with those you don't want to put it directly on your skin because it can blister your skin. But that's an exothermic reaction. It is giving off heat. It's releasing energy. In contrast, an endothermic reaction is a chemical reaction that absorbs energy. And so this is one that when the reaction takes place, it's going to get colder. An example of that would be these ice packs that they use at hospitals, right? If you've ever seen those, it's a little package that, again, you crush it up, a chemical reaction takes place inside, and all of a sudden it gets hard and it gets cold, and so it's absorbing energy in those ice packs, and therefore it is an endothermic reaction. So the last definition that I want to give you, again, is something that you've heard before. I know you've talked about this, at least in physical science: kinetic energy. So kinetic energy versus potential energy. And the words, especially the word potential, kind of gives us some an easy way to remember which one is which. One of these forms of energy has to do with motion, and the other form of energy is energy that is stored, right? So when you talk about someone, you see, as a teacher, you see a student and you're like, that student's got a lot of potential, right? All of you guys, this is what I would say about you guys, right? And that just means, hey, they could really accomplish a lot if they put their mind to it. There's a lot of potential. They haven't done it yet, but there's a lot of potential there, right? And so the idea is that is the ability that's stored up. So when we talk about potential energy, that's energy that is stored. So this would be the one, energy stored, that's the one that's stored. This is the one that is energy in motion, right? So when that energy actually begins to be acted out, then we would say energy in motion. So the classic example that you've probably heard, like I said, in physical science, is that you have a rock, it's sitting at the top of a hill, it's just still, it's not doing anything, but it's right at the top of the hill. If there was just a little push that was given to it, it would roll down the hill and it could do a lot of damage, right? So there's a lot of energy stored in that rock at the top of the hill, but nothing's actually happened. It's just energy stored, so it's got a lot of potential energy. But then if someone gives it a nudge and it starts rolling down the hill, now that potential energy has been converted into kinetic energy because motion is taking place. So just want to make sure that you remember the difference between those two forms of energy as well. So exothermic means it releases energy, think hot hands. Endothermic means it absorbs energy, think an ice pack. Kinetic energy is energy in motion. Potential energy is energy stored. The object's stationary, but it has energy stored in it. All right. Hey, that's it for chapter 13. So we're through another chapter, and I will see you guys in class.